Number theory, very, very, very old branch of mathematics. And it gets down to the idea of the beginning level of abstractions. When we talk about, in the oldest sense, when we talk about numbers, we extend them, but in the end, right? This itself are numbers, right? We start off with 1. What's 2? Well, it's another 1. And we just add one thing at a time. However we choose to represent these, right? When we have things like, and I write symbols, say this, which are Hindu Arabic system in terms of the symbols themselves. The number 8, I might see this symbol, but in my mind, I must think that. Right? It's a collection of these things, and we call it 8. Whatever culture, language, whatever we have. When we had abstraction build up over time, we had 1, 2, and then more. We have things like a couple, words like few, words like a lot, right? These are quantitative words that just, kind of goes up and builds. There's some cultural things, like we have 1 and couple, right? Couple means 2. Right? That's a sound or a word that means 2 things. Now, there are cultures that have 1, 2, and then more than that. That's it. And if you would think about it, when we do anything, we have a reason for it. If the most amount of stuff that you dealt with was usually in pairs, and sometimes more, right? And there are cultures where you have like 1 and 2 and more, and if a person said, well, I want 2 cows for 4 goats, they couldn't do it. They could do 1 for 2 and 1 for 2. They could not do 2 for 4. 4 doesn't even make sense. For us, if we look at abstraction and we work on things over and over and over and over again, sometimes we'll get into the pattern of assuming that these particular symbolic representations of things are the thing. But they're not. And so one of the things that we're going to go back to is this idea, okay, what in the world is number theory? What do we actually do in the most basic sense? Number theory starts off with little kids, like toddlers. What do you do with these sorts of things? For us, in the idea of number theory, yes, our objects really are all the integers, like negative infinity to positive infinity. Even though 0, and under the idea of numbers, right, the actual having of things, 0 does not make sense, right? It's nothing. Why do you need to represent it? What's a negative, right? For us, we are going to deal with number theory. We'll do classic number theory. We talk about positive numbers, negative numbers, and include 0. But we're going to build it from what they naturally came from, which is 1, 2, 3, 4. And then we are going to, okay, now that's my objects. Now comes the concept of, well, what are operations? So number theory is the study of these things that are in whole, right? 1, 2, 3. And what can we do with it? And we'll start off with really simple things. And I won't define, we'll just do what we expect to do. For example, plus, minus, and times. I'm not going to define. Everybody understands what these are, right? What's plus? You take them and combine them, right? And now, on the other hand, I could go down and say, what is really plus? Okay, what is the fundamental thing of number theory? The fundamental thing of number theory is you can count, right? We all have to be able to, because if I look at the numbers are what they are because we can literally count. Why is 2 to the right of 1? Because I have 1, 1. Why is 3 to the right of that? Because I've got 1, 1, 1. We keep successively putting on one more object. And I know how to count. What is plus? Plus is actually counting, right? 2 plus 3, we put it beside each other, we count. 1, 2, 3, 4, 5. That's why 2 plus 3 is 5. I know how to count. What's subtraction? We would take away, right? Which is, right, counting. I've got 5, take away 3. 1, 2, 3. Oh, got 2 left. Right? I know how to count. What about times? It's called multiplication. What does it mean? Multiple addition. 3 times 5 is a 5 and a 5 and a 5. Now, again, what is this counting? Wow, I can count in groups. Sure, 5 plus 5 plus 5 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But if I count a lot, you could count by 5s. 5, 10, 15. So 3 times 5 is 15 because I can count in blocks. In other words, if you count enough, multiplication is just multiple block counting. What's 4 times 7? Well, let's count by 4s 7 times, or count by 7 4 times, right? We just learn to count these things, and we get to the answer. On the other hand, what is 4 times 7? 28. Did you count that?
Yeah.
That was amazingly fast. What did you do? You memorized it, right? If you do it enough times, you do the typical mathematician technique. Just memorize the answer, right? You could count if you wanted to, but you know what the answer is, so don't, right? That's everyday common sense. On the other hand, if addition is counting, subtraction is counting, by removal, times is block counting, and times is like multiple additions, right? It actually adds to a very interesting question. We have another operator here that we normally deal with kids when we throw a calculator at them instead of actually having them do it. And we have a word, divide. But can you think of a human life application that the word divide has nothing to do with numbers themselves, right? If I said divide, what does that word mean? Split apart, right? And so the first thing that I'm actually going to talk about here, 4.1, is going to be, I need to write nicer on this because there's too many I's. D-I-V-I-S-I-B-I-L-I-T-Y, divisibility. And then we're also going to talk about modulus. Both these are of the same concept. Do you know how to share? And in particular, do you know how to share fairly? When I mean divide, I do not mean the arithmetic little kid pulling out a calculator division. We are not talking about division. We are talking about sharing, and sharing fairly. So when I talk about the word divide, I have things like this. You have 3 children that are going to share 6 candy bars. Can they do that fairly? Why? I have lots of yeses. Why? Every kid's going to get 2 candy bars. Well, could 3 kids share 7 candy bars fairly?
If you split the 7. If you split the 7.
But we're in number theory.
So.
Are you allowed to break things? No. So the answer would be no, because everybody would get 2, but there's 1 left over. So what do?
Give it
You eat the 1. Or instead of talking about kids, we could talk about pirates, right? You could simply have things like you have 7 coins, you have 3 pirates. Can they share it fairly? No. So 1 pirate stabs the other 2, and he gets all 7. Now it's fair, right? You play stabby stabby if it doesn't work. But the idea of divisibility, or the idea of divides, is about sharing, right? This was done for a purpose, especially if you look at numbers like that, right? 5 people show up. They want to share. 1 for you, 1 for you, 1 for you, 1 for you, 2 for me, right? You go through all these sorts of things, right? And you watch kids do this. What is math supposed to do? It's supposed to model the real world. What do people do in the real world? They deal. Fairly. This is actually kind of an important, outside of that, talk about ethics. How important is it for you to trust the people you're with? I mean, if you go into logic, they talk about things like the prisoner's dilemma, and we'll talk about that when we get into game theory and stuff. It's like, how do you can't trust the person, but if you do trust the person, if you both act this way, what does it mean, when you're in a competitive environment? Mathematics can model these sorts of things. So you have things like the Nash equilibrium. But in the end, when we're looking at this idea, certain cultures solve this in different ways. If a culture did have such thing as partials, right? And we would have stuff like 1, 2, 3, 4, 5, 6, 7 things. And I had 3 people. Well, what would you do? You would say, well, person 1, person 2, person 3. You would just go through here and say, okay, 1 for you, 1 for you, 1 for you. Oh, I have enough to share again. 1 for you.
Don't think I did.
And then we would do 1 for you. And then we would do 1 for you. Oh, let's say that we had 8, right? Now, do I have enough to give 1 to everybody?
Still
No. So certain cultures would solve this in a particular way. We would say things like, okay, we have 2, and of the 2, I would have to divide it somehow amongst 3 people, and so I would have 2 2/3 per person, right? But how would you do 2/3? The only way to do 2/3 is if I would break each of these into thirds, into 3 pieces, and then everybody gets 2. But then we get to argue about it, because that's a whole lot of little breaks, right? You would sit there and you would look at this and say, wow, a third and a third and a third, and we got 2 of these thirds. So I've got 2 full pieces and 2 little tiny pieces. I don't like that. But on the other hand, I would realize that if I would break each of these in half, now how many halves do you have? 4. So I would do a half and a half and a half, and now I'm down to a half. Now I have 1 object, and I have 3 people. I'll divide it evenly, and so I would get a 1/6 and a 1/6 and a 1/6. So for the Egyptians, they would share this way. Why is this better than 2 2/3? And for other people, we would say 2 point what? What is that? 6, 6, 6, repeating, right? Well, we can't even represent it decimal. Yeah, it's like that. Well, they would do this because what happens? Why? Everybody gets 1 of a whole quantity, right? 1 of a half, 1 of a 6. What's nice about that? They're as big as possible, right? A half is bigger than a third and a third. I give people as large of, if I was paying people in bags of grain, I'm giving them as big of bags as possible. 2 full bags, a half bag, and a 6th bag. Not only that, we can all look at our stuff and think, is it fair? I've got 2 full bags, you got 2 full bags. A half bag is easier to compare to a, look, we all got a half bag. Right? Instead of saying, well, I have a 2/3 bag, and then you got a third and a third, right? Because how would you make 2/3? Pour a third out, then give somebody a full 2/3 and give another person a third and a third, and they would look at that and say, how's that fair? I don't agree with that. On the other hand, this allows people to say, yeah, I believe I've been treated fairly. And it's one of those things when you look into past, too many people, when we look at this stuff that you've done over time, for some reason modern people look into the past and they think the Dark Ages is full of retards. Right? Well, they were dumb. It's like, of course they weren't. They were way smarter than we are in a lot of ways. Why? In what they did. Too often we look back and say, well, they couldn't have built those pyramids. Why? Because I couldn't have built those pyramids without big giant things, so aliens did it. What are you talking about? Just because you can't think of it doesn't mean that they're not smarter than you. Knowledge does not equivalent to ability or intelligence. Just because you didn't live in their culture to see what's going on doesn't mean that their culture is somehow ignorant. So we always have to be careful about that, especially when you look into the past and just simply say, well, they couldn't have done that. Well, they did it. So you're wrong. So as we go through these things, what these mean, it's kind of a little history and math there. What these things mean, we have to rethink what we do. And especially we have to get rid of calculators. We have to think of things in terms of whole amounts. And we have to be able to do mental math. How many of you guys do sharing and adding and counting and work with numbers on a regular basis? Just simply because you live it. People walked into your store and they said, I got this many eggs, I need that, and you're considering, well, I'll take a couple eggs for this. How many of you do that on a daily basis? None? How many people used to have to do that, right? A few. But how many people used to have to do that? Everybody? And so we're a little bit behind the curve.